Hello, my name is Cameron, and I'm going to be showing you today my trajectory solving project in Python. This basically takes two orbits. Well, sorry, let me explain. I work with a group that builds satellites or CubeSats, and they needed something like this, and I thought this would be a good overlap kind of for the Python project in this because it was a really good experience learning Python. What I basically did, I had some Python experience before, so I wanted to make this a little more complicated than it probably had to be. But basically, you give it a bunch of parameters that define an initial orbit, and then you give it another set of parameters that define the final orbit. And between the two, you want to find the optimal trajectory and thrust profile that'll get you from one orbit to the next um, for a satellite with a propulsion system, basically. And so I go through all this code. Essentially, what it does is it uses this Gecko library from, this is all commented out because it's in a class now. I should go to the class. But inside this Gecko, you define this Gecko solver. And if you're doing this, you have to download that pip install Gecko. Pretty easy if you have it all set up. But basically, what you have to do is go and define all the dynamics of the system. So from all the parameters we pass to it, we give it a bunch of stuff that gives it the initial conditions, and then those initial conditions and maximum thrusts and bounds on the problem basically are turned into a set of dynamics equations. So you can see this is based off of um, Newton's law of gravity, right? Or universal gravitation, I suppose is the correct term. We have the mu of whatever the central body we're orbiting times the x value divided by, or the x radius vector, the x position vector, sorry, and then the magnitude of the radius cubed. And that's how you end up with a normal vector pointing towards the Earth. And yeah, it's really actually easy to set up these kind of problems. It uses this background library called AP Monitor. It's actually kind of interesting, but I'll leave that alone. But you give it a cost function, so you say, okay, well, I want to minimize this integral of thrust, so the magnitude of the thrust vector, and then I also want to minimize the time cost. And basically, when you run this, so if I go back to main.py, and I know I'm doing this in Spider and everything else we did in class was in VS Code, but this problem was a lot bigger than VS Code, and I have this already all set up in Spider, so that's why I did it in Spider. I'm sorry if that's a problem. But we run this. It takes about 3 seconds. I just ran it up here. But it'll pull up the plots of the trajectories here. So here's the trajectory plot. And you can see it's going from this initial red orbit to the final purple orbit. And you can see the optimal trajectory that it takes. If you try to optimize for fuel, it'll do this in many more orbital rotations. So it'll go around a bunch until it eventually gets to this final orbit. This just happens to be optimizing for time and fuel usage within the constraints. So if we go back over here, we can see that the X thrust, the Y thrust, and the Z thrust, what those are supposed to be. And the whole point is you'd be able to take this and then output it to whatever the, what do you call it? The thruster you're using is. So you would be able to give it a thrust profile. And with that thrust profile, you would be able to control the satellite to tell it how much to, or how much thrust to put in the X, Y, and Z direction, depending on how you're vectoring that or whatever. You would take this and then turn it into a set of either rotation matrices if for the thruster going in a single direction, or if you had X, Y, and Z thrusters, which some satellites do. Some of them just have a single one pointed out the back. So it just kind of depends. And you have to, either gimbal that or somehow point the satellite in a different direction. So yeah, that's my project. It uses two classes. It uses an orbit propagator class to find the initial class, and to find the initial orbits. And that basically does the same thing as that Gecko library, but with the SciPy propagate library. I didn't make all this. A lot of that came from this guy on YouTube. You can go look up his YouTube channel, but it's Alfonso Gonzalez. So he has a whole thing on astrodynamics with Python, but all the Gecko stuff I did by myself. So yes. Anyways, thank you very much.